Okay, our next
Okay.
speaker is Kaustubh Agarwal, and he will also present joint work with Yogesh Joglikar, who I think has to teach at this time and apologized as well for not coming. And Kaustubh will tell us about exploring the PT breaking threshold in Kitaev chain. So when you're ready, go ahead.
All right. Thank you, Andres and Francisco, for the opportunity. And this has been a wonderful series of lectures. I'm sure next year also we'll get to meet in person in Santa Fe, I suppose. So yeah, I'm a PhD student at IUPUI, and my academic advisor is Yogesh. Yeah, this is how we write in order to promote PT symmetry in our group. This is how we write IUPUI as. So you can see this is PT symmetry. So, but I'm going to tell you something about this lattice chain model that we have been lattice model. We usually study lattice models, and I'm going to tell you about the Kitaev chain at the PT breaking thresholds in the Kitaev chain. And this paper was published in August of this year, so you guys can have a look at that. Okay, fairly elaborate and long table of content. I'm going to tell you a little bit about non-Hermitian lattice models, and then jump right into PT-symmetric Kitaev chain, and then conclude with some results. So as I mentioned before, we usually study lattice models, and these are fairly easy to study because the matrix representation that you can numerically easily calculate using their matrix representations. Now, in this case, you have a bunch of coupled chains with a different kind of couplings, and the blue represents the gain side, the red represents the loss side. And then we find out what the threshold looks like as we move along the chain. And these systems are fairly, and so PT-symmetric systems are characterized by spatially separated gain-loss sites. And so it's easier to realize them in waveguide arrays or coupled resonators, if you like. So you get this fairly characteristic U-shaped structure of the threshold as you move along the chain. And yeah, so we usually study these kind of models. Let me just dive into a very short introduction. I know that this is not, I mean, this slide is not required, but of course it is just for completeness sake. I want to just talk about PT symmetry. So the simplest model that you can think of is basically this dimer model, wherein you have a gain side and a loss side, which has been represented by I gamma and minus I gamma, where gamma is the non-hermiticity strength. And you can see that the energy spectrum, as you increase gamma, has a structure like this, which is prototypical of this system. And then the energy levels coalesce into and they coalesce at this point, which is equal to J, where gamma is equal to J. And this is known as the exceptional point. This is no longer, and this is also this is degeneracy not only in the energies but also in the eigenstates. And as you can see that the angle between them also changes as you increase gamma, and for the angle between them is 1 when you at the exceptional point. Okay, so let me tell you about the Kitaev chain. Now, the Kitaev chain is a celebrated toy model which describes a one-dimensional p-wave superconductor. And but I'm not going to delve much into the aspects of the Kitaev chain, because I mean it's fairly well studied for its topological features. But what we were interested in is if we can sort of model this in a different way, and as a lattice model, and study it in a different fashion. So you can, so here's the Hamiltonian. The mu represents the on-site potential. The J is the on-site, the inter-site coupling, and the delta is the superconducting coupling between two Cooper pairs. I mean, this term is given by the BCS theory, of course, and this is where Alexei Kitaev added the term, this J term, to sort of link the two Cooper pairs. Okay, so if we transform this into the Bogoliubov form with the state with the state vector as represented by this, where C1 is the as I mentioned before, is the annihilation operator on site 1, and C1 dagger is this creation operator on site 1. And if you do the Bogoliubov transform, you can actually you can represent it in the site basis as follows. Now this is important because now looking at this, you can actually draw a picture of what it looks like. And this is the picture that we were trying to get. Of course, now if we add a non-hermiticity term to this, which is given by the which has the gain site on the M naught side, and M bar is the loss side. Now, in order to see this, we can see that it's basically a ladder chain kind of thing, which is wherein the top chain has an on-site potential. All the sites, all the points on the top chain have a minus mu on-site potential, and the bottom one have a positive mu on-site potential. These are coupled using J and minus J, and you have and then you have this cross imaginary coupling, so to speak, between the adjacent chains, sites of the adjacent chains. The mu, the gammas are basically now you split them up as you have two pairs of them, because now you have two chains, because we in the Bogoliubov transform, and now we can actually do some calculations with this. So what we did was we took this Hamiltonian and try to find the eigenspectrum. So now this is still the Hermitian spectrum that I want to show you. But what we want to convey is that the structure of the PT phase profile can be actually determined, is sort of closely related to how the band structure looks like. And you can see that for mu equals 0, this is the band structure. As you increase mu, the band structure sort of changes, and it opens up at it sort of mu equals 2 is the point where it transitions. Now, conventionally, you would see the band structure as the energy versus mu, which is the on-site potential, and delta is considered to be 1, which is equal to J. Delta over J is considered as 1. And then you claim that it has topological features wherein you see these zero energy states, and they are which are localized on the edges, which is what the Kitaev chain is actually studied for, is for the Majorana fermions. But I'm not going to delve into those aspects. We are just looking at the PT threshold profile of this chain. So as you can see that it opens up, and then you have an open structure over here. So now these are the bulks. These top ones are called the bulk states, and these are the edge states. Now, what does the PT threshold profile look like? And so here it is. So for the even chain, what we found was that for mu equals 0, you get this this kind of a PT structure, PT threshold structure. And you can see when delta is 0, just means that these are two uncoupled chains, and you get this prototypical or characteristic U-shaped structure as you do. So M naught basically is when you change the position of the sites, of the gain loss sites. And you can see when the the gain loss impurities are on the edges, you start seeing a rise as you increase delta, and then it suddenly drops and then sort of saturates to 0.5 0.5 gamma over G. When you increase mu, when you start introducing on-site potentials, then it starts to get a little messy. You start seeing these spikes, but the point is that if you increase the number of sites itself, I mean, basically if you approach the thermodynamic limit, these spikes basically go away. And they're fairly noisy when the gain loss impurities are in the middle of the chain. So yeah, and when you increase mu further, mu over J equals 2 and mu equals J is equal to 3 are fairly similar to each other. Okay, so now what about the odd chain? So we do the same thing for the odd chain. And what we find is that, sure, for mu equals 1, it's sort of a little, it's a little bit noisy, but you still have a similar structure. But what I want to draw your attention to is this part, which is when mu is equal to 0, when the on-site potential is equal to 0. You see a striking difference between this and the odd chain and the even chain. Wherein here in the odd chain, what we found was that at the edges, the threshold increases as you increase the superconducting coupling and sort of saturates after a while. But in the odd chain, this sort of continues to rise as you increase delta, and not just over there, but even when the impurities are closest together, which is over here. So it decreases first, but then beyond delta equals 1, it starts to increase. So this is something interesting that we saw, which was not previously reported. When the impurities are closest together. Okay, another interesting feature that we saw was these reentrant phases. So if we just take the this chain, and then also we keep the impurities at the edges, what you find is that for delta greater than 1, you start seeing, and when you increase gamma, you start seeing the PT. So the black region basically represents the PT-symmetric region, and the colored one represents the PT-broken region. If you start at some point for delta greater than 1, you start seeing that the PT breaks and then makes up again, and then breaks again. So these reentrant phases are sort of interesting to see, and but the left pictures are sort of sure. Okay, you can find out what the PT phases are, but what was more interesting was to see what the EP lines were. So we have these lines which actually correspond to the coalescence of two or more than 2 eigenstates. So the black lines that you see over here are basically the EP, the coalescence of these are basically second order exceptional points, and but only at delta equals 1, delta over J equals 1, you get a third order exceptional point, because the states that participate are the two lowest states in the bands, and also the zero energy state is the one that participates. So it's a third order exceptional point at delta equals 1. And beyond that, now over here you can see that you have many second order exceptional lines, and these occur in the bulk, in the bulk spectrum of this chain. So this was fairly interesting to see, and which is sort of important also to report. So yeah, so I think with that, I mean, I can sort of conclude, and these were some fairly cute results to show what was going on. And so we investigated this dependence of gain loss on the Kitaev, on this Kitaev chain. We found a rich profile, threshold profile, and wherein we saw an odd-even difference between the odd and even sites, between odd and even chains. And the cool part was, the good part about this is that maybe we could realize this in an optical setting, wherein we have a coupled waveguide arrays with chains, and then you can probably study this in more detail. And so with that, I thank you all, and I take questions.
Thank you very much, Kaustubh. Any questions? No one has a question.
I guess I have a question. I request a clarification.
Okay.
You said you showed a slide of your dispersion relations, or that's what you called them, but I didn't really get that slide. Yeah, so normally dispersion is in a chain would be your energy versus your quasi-momentum, but you described delta here as your on-site potential. What did you mean by that?
No, delta is the coupling between the Cooper pair. So it's the superconducting coupling, which is basically what this is. Let me just show. Yeah, this part right here.
I see. So it's your pair creation annihilation term is delta. So, but you call those things dispersion relations. Why would you? It's just like a sort of phase diagram of the system.
This one? No, I didn't say dispersion relation. I just said it's an energy. It's an energy plot. Yeah.
Okay. Sorry. I guess the way you described it as band structure. Oh, okay. Okay. Normally that's plotted as a function of quasi-momentum, but I see what you mean. Okay. Thank you.
Okay.
Miroslav.
I just had a small comment on this reentrant PT phases, because it's something which may be understood as sort of absence of sufficiently many parameters. If you have two parameters and you get such a diagrams like in the picture, so you get change of one parameter implies the reentrance of reality and broken symmetry. But in broader space in which you perceive this system as vicinity of exception point, so it's sort of fine-tuning which is needed. I mean, it is something which you understand when you analyze vicinity of exception point as something which is similar to Jordan-Brown matrix, which is non-diagonal. So in this sense, this is sort of artifact of parameterization, and ambition of research should be to find natural parameters which would parameterize this reentrance. Do you have some comment on that?
Not really. So the reentrant phases, and you are right, and it depends if you increase the number of parameters, for example, the gain loss. So now in this case, we had two pairs of gain loss potentials, but of course now they sort of are competing with each other in a way, with yes, they can show reentrant phases. But looking at physical parameters, I'm not too sure how one would go about doing that. Something to think about.
Okay, thank you. It's something like challenging combination between theory and experiment, because you are able to simulate things. So that's a nice thing to study. Thank you.
Correct. Yes. Thank you.
Any more questions, comments, clarifications? This is all fine. Okay. Kaustubh, thank you very much again. Thank you.
Thank you.
Thank you very much.
Yeah, I'd like to make a